Hey guys, welcome. Yeah, so our third example on improper integrals, and here's a fun problem to work on. All right, now to start, we have to use the proper grammar on improper integrals, right? Meaning that we replace this upper limit with infinity. Um, hey guys, welcome. Yeah, so our third example on improper integrals, and here's a fun problem to work on. All right, now to start, we have to use the proper grammar on improper integrals, meaning that we have to replace the upper limit with a constant and send that constant to infinity, right? And so that means that we write this here. And then we recognize that dividing by e to the x is the same as multiplying by e to the negative x. So we rewrite our integral in this fashion, and then we've given it the name a. So a represents the limit as b goes to infinity of the integral from 0 to b of e to the negative x times sine of lambda x dx. And then now it's easy to see that we need integration by parts. So for that, looking at this integral right here, make u sine of lambda x, and then that means du would be cosine of lambda x times lambda times dx. And then, of course, that will mean that dv is e to the negative x times dx. And when I say u and dv, I'm talking about the integration by parts formula, right? Okay, I assume you have experience with that. And I have many videos on integration by parts, so check them out if you need additional practice. Anyway, as I said, dv will have to be e to the negative x dx, meaning v is negative e to the negative x. All right, so then doing the correct integration by parts, our integral is now limit as b goes to infinity, and then this integral here will turn into uv. So that's negative e to the negative x. That's v, and then u is sine of lambda x. So I have vu, but same thing as uv. And then uv evaluated at 0 and b, right? And limit as b goes to infinity affects everything that comes after it, right? And then minus the integration by parts formula, remember, was uv minus the integral of v du. And so minus v right here, and then du right there. Yeah? Okay, cool. Now this minus right here will turn into a plus, right? And just reminding you, there's this minus sign from v being negative, right? Okay, cool. Those are the highlighted items. And so simplifying a little bit, we can write a, which is all of this, like this. And I've distributed lim as b goes to infinity both to this part and then this integral part, right? And so I have it here and here. Okay, cool. Now, where to from here is the question. How about here? Which is, in this first part, we evaluate at b and 0. And that means we plug in b and then plug in b into this quotient and then subtract from that, plugging in 0. And of course, when you subtract, you're subtracting a negative quantity by this minus sign, so I have a plus. But yeah, otherwise I have b plugged in and I have 0 plugged in. Sine of 0 is 0, so this part is going to drop out, right? Okay, cool. All right, and so that means a cleaned up version of my last step is this, getting rid of sine of 0 over e to the 0. And now limit as b goes to infinity of this guy here, right? What is that? Well, notice that sine of lambda b is, or negative sine of lambda b is bounded by negative 1 and 1, right? It's between, its value is between negative 1 and 1, this numerator, negative sine of lambda b. It's bounded. So it doesn't matter if b goes to infinity, it's going to stay between negative 1 and 1. But e to the b is going to grow without bound towards infinity. So we're going to have something bounded divided by something tending towards infinity. So this whole thing, this whole quotient is going to go to 0 as b goes to infinity, right? And so that means then that our integral a is going to simplify to just this here. Okay, cool. So where to from here? Yes, painfully, integration by parts again. All right. So let's remind ourselves of where we left off on a. So we're saying a is right here, and we reckon that we have to do integration by parts again. Okay, cool. But we do need to make space, so let's make space. We do that, and then, as I said, doing integration by parts on this part will mean that we pick a u and a dv again. Why don't we go with u being lambda cosine lambda x, so that's this. And so du will have to be the derivative of cosine, negative sine, and there's the negative, and then the sine of lambda x, and then by chain rule times lambda. So that's why we've got negative lambda squared to lead, yeah? And then, of course, dx, yeah? Okay, cool. So with that u, that's the correct du is what I just said. And that means that dv is e to the negative x dx, right? So if dv is e to the negative x dx, then v will have to be negative e to the negative x, right? Okay, so the integration by parts formula tells us that u dv is equal to uv minus v du, right? Minus the integral of v du. uv minus the integral of v du. All right, and as I said, I have many videos out on integration by parts, so even though I just misspoke and saying uv minus v du, you shouldn't require further explanation. It's the correct formula is the integral of u dv is equal to uv minus the integral of v du, and that's what I just showed here based on the correct u and the correct dv, and therefore yeah, you get it. And so our integral a now looks like this, okay? And again, we have to evaluate in this part at b and then at 0, and then send the limit as b goes to infinity. And then we have this second guy. Now in this second guy, first there is this minus sign from the integration by parts formula, and then there is this minus sign from v being negative, and then there is this minus sign in front of du, so in front of the minus lambda squared. So these two minuses will cancel into a plus, and so that means we still have this minus sign, right? Okay, otherwise we need to evaluate in the first part, and so if we do all that, then I could display this. And because when you evaluate, you're going to do minus a negative quantity here, and that's why we've got a plus here when you plug in 0, right? Okay, it's the same explanation as I offered you earlier when we had to do integration by parts the first time, so you should be able to follow. All right. Now what? Now in the second part, as I said, and the one involving the integral, this minus and that minus take care of each other, but we need to keep this minus sign from the integration by parts formula, and that's right there. Now, lambda squared can come out of the integral, and I've put it in front of the integral, but also put it in front of the limit, because the limit as b goes to infinity doesn't affect the constant lambda or lambda squared. And so we do this, and I did that intentionally because look at this here. What is that? Remember earlier I read it out in full. I said limit as b goes to infinity of the integral from 0 to b e to the negative x sine of lambda x dx is a. I said it's a. So in this part, what we have is minus lambda squared times a, right? And in the first part, well, here I'm going to get lambda times cosine of 0 is 1, e to the 0 is 1, so I'm just going to get lambda from this second quotient. And this first quotient, as b goes to infinity, notice that the numerator in this first quotient is bound by lambda and negative lambda. So lambda cosine of lambda b stays within the values negative lambda to positive lambda, right? It's bounded, this numerator in absolute value by lambda. And the denominator, e to the b, as b goes to infinity, grows without bound. So just like earlier, this here is going to go to 0 because the denominator grows without bound and the numerator is bounded. So this is going to go to 0. And then as I said, from the second quotient, I have lambda. And then I have minus lambda squared times a, our integral that we've been working on, right? So that's this. Well, in fact, I didn't simplify the lambda times cosine of 0 over e to the 0. I'm going to take an extra step. But this is gone because as b goes to infinity, as I said, e to the b grows without bound. Numerator is bounded, so this goes to 0. And then there's this right there. And then minus lambda times a. Okay, and as I said already, this here is just lambda. So that means that we can simplify to this, right? And so I have a plus lambda a squared. So I've added lambda a squared to both sides. It's equal to, and this here is lambda over 1, which is lambda. All right, so that can be cleaned up a little bit like this, which is on the left side, we could factor out an a, which is the integral that we want, we've been trying to solve for. So we get a times 1 plus lambda squared is equal to lambda. And of course, dividing by 1 plus lambda squared on this second to last step, we get the desired result, which is our integral a is lambda divided by 1 plus lambda squared. Yeah? All right, cool. I hope you enjoyed this and keep watching and take care. Bye.